All right, the next model here is the model that involves solids and integrals. Basically, it's going through all of the different iterations that involve an area between two curves that we went over in the last half, in the second half of Unit 8. So you have typically an area R given between two curves, and then the questions are about finding the area, finding the volume of a solid that consists of slices of a certain shape, and or letting the area rotate or revolve around an axis of revolution. So all of these are here. In this case, it's kind of swapped. So find the area of R, right, but do not evaluate an integral expression that gives the volume of a solid generated when R is rotated about a horizontal line. And then the region R is the base of a solid. For the solid, each cross-section perpendicular to the axis is a square. So these are the typical things that you can do with an area between curves. The first step is always identifying which curve is the top, which curve is the bottom, and also deciding if you're going to work relative to x or relative to y. Both is possible. One of them is usually much easier. In this case, it's working towards x, and the functions here, 2x squared is a parabola that is concave up. So this bottom function here is f of x, and the top function is g of x. So let's find the integral or the area on A. The area on A, and I'm going to split the integrals because I want to use u substitution for this convoluted cosine function. So I'm going to just make it separate. The g of x is the first one. So 0 to 2 of 4 cosine of pi over 4 x dx, and then minus the integral from 0 to 2 of 2x squared minus 6x plus 4 dx. So this here is the total area. And now I'm going to do the integration. So I'm going to do first this one here, just focus on the first integral. And I'm going to use u substitution for that one. Although I find it simple enough to do this straight ahead, but let me just do u substitution for this part, and then we'll see what happens. Okay, so that's pi over 4 dx. In other words, dx or du times 4 over pi is going to have to be substituted for dx. So then I can substitute. So this thing here is the integral of 4 cosine u. Now dx, I have to substitute this thing here. So it's 4 over pi du, like so. And let's just keep the equal sign going here. So I'm just going to keep the second integral here from 0 to 2 of 2x squared minus 6x plus 4 dx, like so. And now I have to still do the boundaries here on the first integral. So if x is 0, then u is also 0. So this bottom interval here, or bottom boundary, stays the same. And if x is 2, then u is 2 times pi over 4, which is pi over 2. So pi over 2 is the top boundary for this first integral here. All right, so I'm still looking at an expression that is completely representing the area of R. Fine. So now let's find the antiderivative, sort this out a little bit. Let's pull all of this stuff that's constants in front of the integral. So we're going to have 16 over pi, right? 4 times 4 is 16 over pi. I'm going to pull this out in front, and then I'm going to find the antiderivative of cosine u du, because that's the only thing that's left on the inside. Antiderivative of cosine u du is simply sine of u. And then I'm going to put the boundaries on here from 0 to pi over 2, like so. And then back here, I'm going to find the antiderivative of this thing. So this is going to be, let me put big parentheses on here so I don't get in trouble with this negative sign. So add 1 to the, use the negative power rule for, or inverse power rule for each of these. So x to the third and then divide by 3. That gives you 2/3 of x cubed. And then here, x squared, and then divide by 2. That gives you 6 divided by 2 is 3. And then plus 4x. And we don't need the c because we're putting the boundaries in there, and the c's are going to be eliminated, right? And here I use these two boundaries, 0 and 2. All right, I'm getting closer. I'm getting closer. All right, so here we're going to have sine of pi over 2. Let's see, sine starts in the middle, and then, I mean at 0, and then pi over 2 is going to be 1. So that's 16 over pi. And sine of u, sine of 0 is going to be 0. So I don't have to subtract anything. Let's just write it here anyway, so we have it accounted for. And then minus, still keeping the big parentheses here. 2 inserted into this here is 8. 2 cubed is 8 times 2 is 16. So that's 16 over 3 minus, and this is going to be 2 squared is 4 times 3 is 12. And then plus 4 times 8, that's, I mean, 4 times 2, that's 8. And then this 0, inserting 0 into this will turn everything to 0 again. So just going to put 0 here at the end. I guess technically this parentheses goes here. There. All right. Okay. Gosh, these problems are taking long, but you have plenty of time for this, so don't panic if it takes a long time. That's fine. So we have the end result here is going to be 16 over pi minus, let's see what this is. So minus 16 over pi over 3. So plus 12 minus 8, I guess that's plus 4. So 4, this can be simplified a little bit more. 4 is 12/3. Let's do it. So that leaves us with minus 4/3. So it's 16 over pi minus 4/3. And that is the area of R. Nice. Okay. Write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 4. Okay, so the horizontal line is right up here, and I'm rotating the R, the area between the curves around this axis up here. So my radii, I have to first identify the radii. The big radius is the one that is from the, from the axis of rotation to the function that is farther away from the axis. So it's going to be 4 minus this piece here. So it's just from here to here, right? And this function is f of x. So let's just write the concept here. So the integral big R is 4 minus f of x. And I'm going to have to square that R and put dx here. And of course, I'm getting a circle from this by multiplying it by pi. So pi r squared, this is big R squared. And then subtract from that, the radius is, the little r is 4 minus the area, 4 minus g of x. So this is minus pi integral. Oh, integral has to have boundaries here. 0 to 2. And the inside is 4 minus g of x squared dx, like so. So right, but do not evaluate an integer expression is wrote about that. So that's it. That's all there is to it. So volume, you can simplify it, but you don't have to actually. But since all of the boundaries and the pi factor is all the same, so you can say 4 minus f of x squared minus 4 minus g of x squared dx. So either of those forms of the volume are acceptable and correct and give you the full points. And C, the region R is based on the base of a solid. For this solid, each cross-section perpendicular axis is a square. So for that one, you just go for the solid. So it remains now g of x is the top. So you have the solid from 0 to 2, g of x minus f of x. And then this whole thing needs to be turned into a square, right? That gives you the square of the baseline and dx. So this time here, volume is this thing. And let's see, anything else here? Right, but do not evaluate an integral expression that gives the volume of the solid. So that's it. So actually, in this case, A was the far more extensive part of the problem that took a lot of time. And the other parts here are more faster and more simple. So here you can see, starting from C and B, you can write the expression as the actual functions, or you can write it in this format as we have. So either one is acceptable and gives you the full points. Integrants, the limits, and the constant is it. Constant here is, I don't know what they mean by constant in this second case, but the constant, I think this is just kind of like a copy error, because there's not really a constant in this one. The constant is here, which is the constant that gives the area of the axis of rotation. All right, so then let's double check the area A. Area is g of x minus f of x. So g of x is cosine minus f of x, so that's correct. And then finding the antiderivative here. Okay, so they actually just kind of did it straight without u substitution. And yeah, so usually when you have just a simple factor and you don't have anything else here, you can also find the antiderivative directly without going through u. So if this is your original function, the antiderivative of that would be 4 sine of pi over 4x. And then you just have to adjust for the factor of pi over 4 that you'd have to multiply this when you take the derivative of this, right? So that means you have to add the inverse of that inside factor as an outside factor to the function, and that gets you to this, right? You see, so now if you find the derivative of this thing, you get 4 cosine of the inside, and then times pi over 4, that cancels out the 4 over pi, and you get this as a derivative. So this here is the antiderivative if you want to just keep it straight without going through the u substitution, but your result is going to be the same, you see, because this antiderivative also gets you that 16 over pi in front of the sign, and then in this case, you still have to compute the pi over 2 from, putting in the correct value 2 up here if you do it by x. So it's all the same, about the same amount of work. It just kind of depends on which method is easier for you and faster for you to do without getting confused. So, that's the other part of it, getting confused because you're picking a method that is storing too many moving pieces in your brain while you're working through the problem can be dangerous. So just pick the one that you like and prefer.